Yeah. Good evening to all. Welcome to 12th week of Electrical Machines 2 NPTEL TA course. So I am Sai Krishna Mulpuri. So today we will be discussing the last topic of our Electrical Machines 2, and it will be on synchronous machines only. So last week we have started the discussion on synchronous machines, and today we will be seeing a very important topic, and it's not only important for your course but also a very important topic for with respect to GATE exam. So during GATE exam, on this particular topic which we are going to discuss today, there is a high probability that direct questions would come from this topic, which are theory based. Theory based questions from this topic would definitely be there if you can check the old GATE papers as well. Once we are at the end of today's discussion, you will also be comfortable with this topic, and you can then go and check back the old question papers of GATE, and you will find at least one question from this topic, which is a direct theory based. And I assure you, this will be very easy if you pay attention to today's discussion. So, yeah, so let's start today's discussion. Yeah. So what I'm saying is today we'll be discussing about a small concept within the synchronous machines, and that topic is effect of variation of excitation of a synchronous machine. So we will be looking at both synchronous machines, that is generator as well as the motor, and the main concept is what is the effect of variation of excitation. Excitation means here we know the construction of a synchronous machine here. We know there is a field winding and also the rotor stator winding, and the field winding is which is wound on the rotor, and that winding we know we are giving a DC supply to it. Now that is what we called as a DC field current flowing through that winding. Now what happens when we vary the field current? That is what we are going to discuss today. Effect of variation of excitation. Very, very important topic. And I would request you all to pay attention, and let's discuss this simple but important topic. Okay. Okay. Effect of variation of excitation. So here excitation is nothing but DC field current. Okay. Now we will be varying the DC field current, and we will see what happens in a machine. So yeah, first we will be looking at a generator mode, and we will also do it for the motor mode. Now, just for assumption, so the analysis remains same, but for just the simplicity and also the assumption, we will be assuming that the resistance part within the synchronous impedance will be negligible. I mean, I'm writing here 0. So we know ZS is equals to RA plus JXS. We assume that this is very negligible, so that we will have only reactance in the impedance. So that is for just assumption. But anyhow, resistance will also be there, but it's very, very small. For simplicity purpose, we are just assuming the resistance to be negligible here. Okay, now let's first look at the generator mode, and then we will implement the same concept to the motor mode. Both are easy. Okay. Okay. So we know how. 1 second. Yeah, we just discussed how a construction of a synchronous machine would be. I'm just drawing it here. So let's say this is our field winding, and yeah, here we have our stator winding, and yeah, the current flowing through this winding we call it as field current or the DC field current, which we call. So this is the field winding, and the current flowing through it will be IF, which is our field current. And now this stator is what connected to the bus. Okay, so this is a bus. So we can say that bus voltage is always constant. It's like a grid. So to which all the loads are connected, where we talked about in the last week. So bus voltage is something which we don't have the control of. It will always be constant. It's like a grid voltage, and we have connected our synchronous generator to the bus, and this is our field winding through which our excitation current, that is DC field current, is flowing. Now this is a generator. Generator means what? So we have to drive the rotor by some means of a prime mover. So that is clear. Now, prime mover is what? Something mechanically rotates the rotor. Now, how like what kind of device is this prime mover? We have heard about this prime mover word a lot, but what exactly is a prime mover? What is a prime mover? So this prime mover could be of many types, but the purpose is it should rotate the rotor. It should give the mechanical rotation to the rotor. Usually, the prime mover could be a steam engine or steam turbine or water turbine or diesel engine, anything. But its purpose is to we will have to turn the rotor. So how does a turbine turn the rotor? We'll have to pump more steam onto the turbine so that it will convert this energy into some mechanical energy, and it will rotate the rotor. So that's how the prime mover usually works. That's how in the big power plants and all, prime mover is what steam turbine, steam engine, diesel engine, anything. Now let's say we have connected our machine, which we are seeing here, to the bus, and then we have increased the steam input to the rotor. That means my steam turbine, which is taking steam as an input, I have increased the steam input to the rotor. So what it will happen eventually, some current would flow into the rotor. That means power will be generated because current has flown into the bus. So from the generator, some power I have supplied to the bus. So whatever loads connected to the bus, some part of it I am able to supply. Some part I am able to contribute from my particular generator which is connected to the bus. Okay. Now let's say my steam input is constant. So whatever input I am giving to the motor is constant. That means what it means it the real power input from the mechanical side is constant, because the mechanical side which you are seeing here is the prime mover side. So from this prime mover side, I am giving only X amount of steam. So that is fixed now here. Now let's say I have fixed the steam input. So the real power input from the mechanical side is constant. It means that my output power delivered to the bus also constant. So whatever input I have given, real power input, excluding the losses, excuse me. So yeah, excluding the losses, the output will be delivered to the bus. So if I fixed my input, my output is also fixed. Not exactly same, there are losses, but output is also fixed. Now my input steam input is fixed. My real power, that means my real power input from the mechanical side is constant. So my output power delivered to the bus is also constant. So the case which I'm assuming here is constant power input and constant power output. Constant power input. That means from the mechanical side, so this would result in a constant power output. So we have to talk in terms of real power, that is useful power, constant real power input and constant real power output. Now, if we see the per phase equivalent circuit for this machine, it's very simple. Synchronous generators per phase equivalent circuit will have only an excitation voltage, a bus, and also in between the reactance. Since we assumed our resistance to be zero, now let's draw the synchronous generator per phase equivalent circuit. So this is what excitation voltage EF, and this is XS, or you can say JXS, and the it is connected to the bus. Okay, yeah. Now this is the equivalent circuit, per phase equivalent circuit. Therefore, for a constant output real power from the circuit, so if you see the circuit, we are fixing the constant output power, real power here. So what is the output power for equation? Sorry. So here we know that output real power is constant. So we also know this is the output. So this is the output side. And since it's a generator, the current direction will be like this, right? Now this is the output voltage and this is the output current. Now my three-phase output will be 3 VIA cos theta, where theta is the power factor angle. We know that. So here it's the angle between V comma IA. Yeah. So this is the power factor angle. Now what is V here? V is the bus voltage. It's always constant. It's a constant value. Now we also know some other formula for this output power. So what is it? Anyone can remember? Last week we have discussed it. I am writing all the two formulas. One I have just written 3 VIA cos theta in terms of excitation voltage and also bus voltage 3 EFV by XS sine delta. So I hope you remember this formula. So delta is the load angle, that is between angle between EF and V is the bus voltage, XS is the synchronous reactance, and sine delta is the sine of the load angle. Load angle is nothing but the angle between EF and V. Now, if we recall, so this is an important formula. This is what we are making it constant because we have fixed this constant. Okay, these expressions are constant now. Now, if you recall from the basic machines formula of the excitation voltage EF, what is EF? Root 2 pi. I hope you remember this formula. Supply frequency multiplied by flux per pole multiplied by the window factor and the turns per phase. Now, this is what we already know. We know that EF is nothing but this one, root 2 pi f k phi kw n phi. N phi is equal to the turns per phase. Now, here what we are varying now? From the figure, if you see the top figure, we are varying the IF here. So, if you see IF, without changing the input or output power, we are trying to change the excitation, that is the DC field current. We know that IF is proportional to field. So this is the DC field current. Now my field will change because it is proportional to IF, this field current. So field flux will change. Now, as I am changing the field current, my flux per pole phi F will change. That is definite. That's I'm sure about. Now, if we vary the field current, what I can say, proportional flux changes, and if you see, apart from flux, all are constants. Root 2 pi, supply frequency is fixed, kW is fixed, turns is fixed. Now, if I change phi f, my excitation voltage will change. Now, if I vary field current, I will say that my induced EMF in the generator will change. If vary field current, right? Now, this is the straightforward relation between DC field current and also the excitation. Now, see, let's see a very interesting discussion now. Whatever we have discussed till now is very straightforward and simple. I hope you all understood till this point. Now we will see a very interesting discussion, that is the phasor diagram of whatever we have discussed till now. That will be the phasor diagram. Now let's say I will just draw a small circuit here just for reference. V, and this is EF and XS, JXS, and this will be the IA. Okay, let's say I have V. This is the bus voltage. Now this is the bus voltage I have here, V. Now at some excitation, I am already have some excitation. Now field current is fixed. Let's say starting initially there is some excitation is there. Some excitation is already present, IF. With at that particular excitation, let's say my IA is here. Now if it is V, this is V and this is IA, the angle between these two will be what? Theta, which is a power factor angle. Now let's say this is all initial conditions, like initial it is IA1 and the initial power factor angle is theta1, and no point in writing V1, V2 because V is always the bus voltage, it is always constant. Okay, now I have this particular condition right now where IA1 is there at that instant of time with an angle of theta1, which is a power factor angle. From looking at the figure, we can say that my IA is lagging V. That means we are delivering a lagging power factor load. Okay, so this is a lagging at particular theta. I am delivering a lagging power factor load. Okay, but from equation, what we have written, I'm once again writing. So let's not go back to previous slide every time, but I will just write it here. Cos theta, which is EFV by XS and delta. Okay, so this is what? This is what is constant. Okay, now from these equations which you are seeing on the screen, the output power has to remain what? It has to remain constant, right? Okay. Therefore, since my output power is constant here, no matter how much you play with the field current, let's say I'm increasing the concept itself we are discussing today is the effect of varying the field current. Now, no matter what field current you do, increase, decrease, or keep it same, whatever value you give to the field current, your IA cos theta from this formula, you see this one 3 VA cos theta, it has to be constant. 3 is constant, V is constant, IA is not constant, of course, but in order to make this as constant, this product of IA cos theta has to be a constant value. Now, for whatever field current you give, this product IA cos theta should be constant because my output real power delivered to the load is kept constant. That is clear. Now, in other words, but we understood that IA cos theta should be constant. But seeing the figure, can anyone tell what exactly is IA cos theta? This is IA and this is angle between V and theta. So what is IA cos theta? Isn't it the projection of IA onto V? This particular, this one, this, that length, the projection of IA onto the voltage axis is called the IA cos theta. So that has to be remain constant. Now, whatever might be the value of IA might be this, IA might be that, anything, but the projection has to be this one. This has to be constant, this length. So in order to have this length as constant, what is the condition? Your tip of IA, this is the tip of IA. It should always remain on this line only. Why? When your tip of IA stays on this line, so let's say you have IA this now. What is the projection of IA on V? IA cos theta is this only. If it is IA is like this is the projection. Whatever might be the IA cos theta will be this only. So you are maintaining IA cos theta is constant. You are bound to keep it IA cos theta constant. So this is the locus of the IA, this dotted line which I have drawn. Okay. Now this is V, this is IA1, this is theta1, and this is the IA cos theta. So this has to be constant. Okay. Now the tip of the current phasor IA, we already said that it must stay on that line which we are seeing here. So because that determines the length of IA cos theta. So whatever might be the IA phasor, your IA cos theta will be same. So such that by drawing a dotted line like that, we are saying that whatever might be the excitation, your IA cos theta product should be constant. Okay. Now let's draw the excitation EF. For a generator, what is the EF equation? EF is equals to V plus J IA XS. Resistance is all neglected here that we already assumed in the first discussion only. Now EF is equals to V plus this IA XS drop. Now we know IA. Okay, let's so IA is like this, and IA XS drop will be perpendicular to this IA. So that we know. Now we have to draw. We have to find the where is the EF one. No. Let's draw the perpendicular to IA X1. So here it will be like this. So here it will be. This is the IA axis J IA axis drop, and V plus J I axis will give you the resultant. Now this would be EF1. Okay, the angle between EF1 and V would be delta 1. Now we got all the parameters, all the operating points in the initial condition. So what are the parameters here? EF1, IA1, IA1, theta 1, delta 1, and V. Anyhow, V is constant. So these are the IA1, VF1, theta 1, delta 1. These are the initial conditions. And IA cos theta, we know that has to be constant on that line, whatever might be the excitation you give. Okay. Now we have drawn the excitation, that is EF1 we have found. Now from the equation, this particular equation, I again write here 3 EF V by XS sine delta. This is also constant because this is also output power. Now 3 is constant, V is constant, XS is constant. Now what needs to be constant? This product EF sine delta needs to be constant because I already told that our output real power should be constant. Now what I am saying is, from the first condition we got IA cos theta product should be constant. From the second formula we got that EF sine delta needs to be constant. Now what is EF sine delta from the figure? So EF is this one, this is delta 1. Okay. EF This is EF cos delta, and this is EF sin delta. Whatever you see, this one, this is the projection of EF onto vertical axis. That is the sin delta projection, EF sin delta. This has to be constant. So by looking at the phasor, we can say now EF sin delta is the vertical length that we are seeing on the figure, and that needs to be a constant. Now, if we increase the field current or if we decrease the field current, my EF should remains my the tip of EF should remains here only, here or here or here or here, anywhere, such that my EF sin delta would always be constant. Okay, now we have set up all the required conditions. Now we will see what happens with the variation of field current. Now the first instant, let's increase the field current. Increase the field current. Okay, now I have increased my field current. Now from the formula we have written in the previous slide, EF is equals to root 2 pi phi F and kW and phi. If I increase my field current, my excitation will, I have written the statement also at the bottom. If we vary the field current, induced EMF in the generator will also change. Now if you increase the field current, you are increasing the excitation. Okay, yeah. Now my EF has changed. Now, since my EFs are changed, these are no longer my operating points. EF1, IA1, theta1, delta1 are no longer the same. They are changed now because I have changed the EF2. V, anyhow, it is constant, but EF2 is changed now, right? Now, since I know my EF1 tip stays on this line only, where it will be now? Does it have to be this here or here or here, somewhere here? I have told you that I have increased the field current. Now can anyone guess the position of EF? Does it lie in this part or this part? It has to be this one or this one. So what is it? Okay. Now I will discuss. Someone has to say something. It has to be left or right. Okay. I told you that I have increased the field current. Now when I increase the field current, my excitation EF will also increase based on the formula. Now previously this is the length of EF from here to here. Now I have increased the length. So it can't go behind this. It is length is decreased here. Now the length should be more than previous. Now it has to be like this. This is my EF2, right? Now we are doing the back process because we have to find where the IA lies now. Uh, Previously it is lagging power factor. Now we have to see where it is lying now. Okay. Now we have located our EF2. Now we know EF2 is all equal to V plus JIAXS. Now whatever between, this is EF2 and V, whatever between EF2 and V has to be my JIAXS drop. This particular, this has to be JIA2 XS because I know this is EF2, this is V. The connection between V and EF is nothing but the algebraic vector sum of V plus JIAXS. So I know this is V. So the phasor joining V and EF should be JIA2XS. Okay, now I have located the position of IAXS drop. Now to find back the IA2 from this point, I am trying to find where it is IS. Is it IA2 is here or is it IA2 is here? I have to know. But I know the tip should remain on this line. Okay. Now how to find this IA2? So this is IA2 axis. Now it has to be a perpendicular projection, right? IA2 axis is always a perpendicular projection. Now if I draw a perpendicular line, this is IA1. Now if I draw a perpendicular line from here, this is perpendicular line. Now and also I know it has to lie on this tip. So the intersection point would be my IA2, this one. Because I know JIAX2, IA2 axis, and with that as a perpendicular projection, I have to find back the IA2. Now this is my new IA2, and the angle between V and IA2, this is my new theta 2. Now, what are the operating points? EF2, first I have drawn EF2, and then I have drawn the JIA2 axis drop. With that, I have found IA2, and then I have found theta 2. Okay. Yeah, once we draw the EF2, we are already sure about delta 2. EF2 is angle. Delta 2 is angle between EF and V. So delta 2 and V. V is always anyhow fixed. Okay. Now we have seen how my EF1 and EF2 limits and also how my IA1, IA2 limits are being limited here. Because I know since my output power to remain constant, these two are the locuses of IA2 and EF2 tips. Okay, fine. Now, if we see here, these are the new operating points which we have got when we increase the field current. Now, let's do the other condition. Let's decrease the field current. Okay, since I did previously I have increased, phi f increased, and EF increased. Now I have decreased, that means flux per pole reduces and my excitation will go down. Now since we know excitation is reduced, so previously it is this one and it should be somewhere here, right? So this has to be the new EF3. Now I have known the position of EF3 because EF3 should be smaller than my V because I have reduced the field current here, and that is EF3, and my angle between EF3 and V should be my delta 3. And since I know EF3 and V from the generator equation, EF is equals to V plus JIA axis, I will know the IA axis drop. So this is this one, V plus JIA3 axis. Okay. Now what is the projection of IA3 axis here? Because this one is the perpendicular now, JIA axis drop. If you project a line like this and also a line like this, it has to cut this locus somewhere. Okay, previously it did cut here, but in the back side there is no point where it will cut. But on the top side, see this one. This point is the intersection of the perpendicular projection and also the locus, because we are already sure that that is where my tip of IA would lie, and also there is the perpendicular projection. From this position, let's draw the value. Now this is what my IA3 is, and IA this is what my theta 3. It's the phasor circuit seems to be complex, but it is very simple when you know your EF sine delta. EF sin delta and this product IA cos theta should remain constant. Excuse me. Okay, sorry. Now once we decreased, we have calculated EF3 now, and then we immediately got delta 3, and then we got the IA3 excess drop. From there we have located IA3, and then we got theta 3, and finally bus voltage, it is already a constant. Now what are the power factor conditions here? Let's look at the let's analyze this complex phasor diagram now. At the initial condition, we know we have a lagging power factor, but because V and IA1 has a lagging power factor theta 1. And now if you see the operating point number 2 for all the 2, so this is where IA2 is, and the angle between V and IA2 is theta 2. It is also lagging. And what about over-excitation and under-excitation? So when can you say it is over-excited or under-excited? Last week we discussed. It can be said by the length of EF and the length of V. Now this is the length of V from here to here, and IA1 and IA2, if you see the first two operating points, this is the what EF2, and this is EF1, and this is EF3. From the diagram we can say that EF1 and EF2 are bigger than these. Obviously it is after the V, and EF3 is before V, and it definitely is lesser in length compared to V. Now EF1 and EF2 are more, then we say this condition as a over-excited, because EF excitation voltage is more here. So for the both condition 1 and condition 2, it is over-excited. And coming to condition 3, see IA3 is here. This is my theta 3. Here my current is leading. We are supplying a leading load. We are drawing a leading current and supplying it to the load. Now here the power factor is leading power factor. What about the excitation? Here my EF3 length is less than EF, so it definitely comes under excited condition. So these conclusions which we have drawn are very simple, but they are very important condition. Now if you want to operate your synchronous generator near to a leading power factor or something like that, you know that you have to under excite it, because your synchronous generator can never be a over excited state while giving a leading power factor, because that's how the phasor is, that's how the rule is. Now by seeing the phasor diagram we can say that for a synchronous generator in the under excited condition the power factor would be leading. For a synchronous generator in the over excited condition my power factor will be lagging. So these kind of theoretical questions are very important. They will directly be asked in many competitive exams and also gate examinations. For 1 mark questions they will directly ask these questions. You shouldn't lose your marks here because they are very simple, and you can by just drawing the phasor diagram you can say, or you can, if you want to remember also you can remember, but I would always prefer going with the phasor diagram. You just say under excited, you draw EF before V and draw the IA axis drop and projection of IA and just find the IA leading or lagging. It's very simple. Okay. Now usually in industries it is preferred to run your loads near to unity power factor, because you always want a very good power factor. if it is a lagging or leading, you have some kind of poor power factor. But if you are able to operate very near to the unity power factor, so what is unity power factor? Unity power factor means unity is 1, power factor is cos theta, cos theta is 1, cos theta is 1 means theta would be 0 degrees. So the angle between V comma Ia should be 0. So if this is V, and where, if this is I, then only if the V and I, they should be in the same phase, then only we can say it is unity power factor. So if we can able to operate my generator where Ia is here almost close to unity power factor, then we can say my synchronous generator is having a unity power factor. That's usually preferred, such that my generator will deliver same amount of power but at the unity power factor condition. Okay. Now with all the analysis which we have done till now, we can actually make an observation figure. That is usually you also do this experiment in your laboratory also. It is a very simple experiment, and it also has a very famous and popular name which we call as a V curves of a synchronous generator. V curves you might have heard. That is nothing but whatever we have discussed till now. It's very simple. Okay, V curves are between field current of a DC winding, that is a field winding, and the armature current flowing through the machine, that is IA. This is also a very important problem. What are the axes of V curves? Very simple. You have to keep in mind. So we are observing the variation in the armature current by varying the field current. So here the independent variable is field current. We are varying the field current and observing the change in the armature current. So on x-axis we have field current and the y-axis we have the armature current. Now we can see actually a V kind of curve in this while we vary from IF from here to here, because this particular y-axis shows the length of IA. Now I know this is V and this is IA and this is the locus of IA. Okay, so this is the length of IA. Now this one is also IA and this one is also IA. Now see, the length is minimum here, right? Always this is minimum, and all the other values of IA would be greater than this IA. So IA would be minimum. The length of IA would be minimum at what power factor? This is at unity power factor, we just discussed. So let's say this is unity power factor point. Here you would have the minimum IA. Now from that point, if you increase the IF, this is x-axis is field current. Now from that point, if you increase the field current, you will have what? You are having the over-excited condition. Over-excited condition means you will have this one. IS will be downside of this one. Now from here, if you increase, your IA length will increase, this one. Now behind this point, if you reduce field current, even if you reduce field current, your IA would go up. The length of the IA would increase. Here also, you will have an increase. So this is what? This is this, all this area is one area and all this area is another area. So this is the unity power factor. Now tell me, what is the power factor in this condition where you have reduced the IF? Reduced the IF means what it is? Under excited condition. From this point you are increasing the excitation, that is you are over excited condition. I will write it here. It is for synchronous generator. Now for the under excited condition, what is the power factor? This is unity power factor. So something should be lagging and something should be leading. So what is the side here? Now go back to the figure. Now for the over-excited, EF1 and EF2 are over-excited. From the over-excited, what we have seen? The power factor is always lagging because IA1 and IA2 are bottom. So theta 1 and theta 2 came to be lagging. So overexcited, this is a lagging power factor. And underexcited, let's look back at the circuit. So EF3 is underexcited because EF3 length is less than V, and EF3 corresponding IA3 is on top of V. So we got a leading power factor there. So underexcited, we will have a leading power factor. So this is very important curves, but at the same time, you might already have seen how simple are these curves, right? Now what we have seen now, we have taken a condition of a synchronous generator. We are actually observing what happens if I vary my field current. That is what happens if I vary my excitation. But the condition is I am not going to disturb my power. I am not going to disturb my steam input to the generator. It is fixed. So since it is fixed, my output power is also fixed. So my output power equation is that if it is fixed, my Ia cos theta as well as EF sin delta needs to be constant. With that, we draw a phasor diagram where the initial operating points are EF1, IA1, theta1, delta1 and V, where we have to get a lagging power factor, and we actually saw that for a lagging power factors, the EF1 turned out to be length more than the V, stating it to be a overexcited condition. Now with we have increased the field current from that point, and then we have decreased the field current from that point, and we have seen the phasor diagram. We came to know that when I increase the field current, I'm actually overexciting the machine. Excuse me. And I have got a lagging power factor. Now if we decrease the IF, I am making my motor underexcited, sorry, generator underexcited. Okay. So for the leading power factor, when I've reduced the IF, actually I have underexcited my motor. And for the underexcited conditions, what we have seen, it is a leading power factor. And with that analysis, we have drawn the V curve of a synchronous generator. V curve, because it's in the shape of V, that's it. No, nothing special about that. Now, see, we have seen how the V curve is changing. And as a conclusion, I will write it here. Synchronous generator will have two conditions, that is overexcited state underexcited state. Overexcited is at a lagging power factor. Now underexcited is at a leading power factor. I want everyone of you to note it down or remember it, or you can do anything, but I want everyone to keep this in your mind while solving the problems, and this is very important for your gate examinations as well as many competitive examinations. Okay, now this is at some constant output power, right? So we have fixed the output power and then we have changed the excitation. We have got this curve. Now I will fix some y constant power. Let's say previously it is some x kilowatts of output power. We have got this curve. Now from y kilowatts I have fixed, again I have changed, I will get some other curve. So when you do that, you can observe that you will get this kind of curve. Because you will get unity power factor somewhere else, not exactly at the same point, but somewhere else. And for some other point, you can see like this, some other curve like this. Now, all these points, if you see, what are these points? This point, this point, this point. These are the locuses of the unity power factor armature current operating points. So these points are very, I can say, people actually like these points. They will plot the current, they will find the current at which the motor will be almost run at the unity power factor, and they actually try to run their motor at this current. So yeah, this locus actually tells that. So yeah, so this one would be at power output 1, and this will be power output 2, maybe this is power output 3, like this, different power outputs curves, different V curves. So yeah, this is the conclusion of our synchronous generator. Okay, now let's see a similar kind of analysis for a motor case also. Now, since generator case we have seen it in detail, synchronous motor case we won't be going in that detail, but it's the same principle and same thing, everything. So we will also see how similar is a synchronous motor analysis to a synchronous generator. Now, first thing for the motor is again we would have a excitation voltage, since we have neglected resistance, and this is my supply bus. Okay, in the motor case, what it will do? Actually, your excitation source, your synchronous motor would draw current from the supply. It won't generate and provide to the bus, but it draws the current from the bus. Okay, so this is IA in this one. So it is drawing the power. Now here the V is what? Bus voltage, and your IA here is the armature current. And okay, this is the per phase equivalent circuit for a synchronous motor. Now, motor should drive some load. Okay, it will draw the power from the supply bus, and to the motor shaft I am actually connecting some kind of load which I want to run. Okay, now I would turn this I would drive this load by taking supply from the by taking the power from the supply. Okay, now what is the motor equation here? EF would be V minus JIA excess drop. This is the basic motor equation. Okay, now here we will vary the field current, and we will see what is the effect of variation of field current uh, uh, on the machine. What happens when we vary the excitation of the machine? Now, same analysis we will do. Let's say initially we will take some operating points, uh, EF1 and delta 1 and theta 1. Sorry, IA1, IA1, theta 1 and V. Anyhow, it's constant. Okay, again I have drawn V here. Let's say it is supplying a lagging load ij1, and this is the theta 1, and since my output power and input power are fixed, my ia cos theta product is constant, ef sin delta is equals to constant. These two are not equal, but they are constants. Okay, don't confuse with that. They both are not equal values. They don't have same values, but the product is constant. Okay. Now, since I fixed the IA cos theta, I have fixed this locus. Okay. Now, with this, what I can say, this is what a condition we are given. Let's say I have now given the excitation. Let's say we have increased the excitation current. Now here, okay, let's draw for EF for this case. Then we will increase the current. Okay, so this is IA, and okay, now IA excess drop we have, that is the perpendicular to the IA1, IA1, this one. This is the IA excess This is how it should be. But we have to subtract this from the V. So here see, V minus JIAXS will give the EF. So this has to be positive and I have to subtract this from here. This is minus JIAXS. And now V minus JIAXS will give you the EF. Okay, actually this, okay. This is EF minus JIAXS give. This will give the resultant is V. Okay. Now what is the angle between EF and V? That is delta 1 and this is EF1 and yeah, these are the operating points at the initial condition. Now we can see this is a IA is a IA cos theta is constant. This one cos theta is constant and also EF sin theta. This is delta EF sin delta, right? This is delta and this length, this is vertical length would be EF sin delta. So these two needs to be constants. Now let's say I have increased the field current. This means that IF increased, phi F increased, EF will increase, that remains same. Okay. Now where should my EF2 would come? EF is increased now. EF would come here, somewhere here. Okay. Let's say this is my EF2 and EF2, now I know EF2 plus JIAXS would take you to V. Now from here I know this should be my JIAXS. This is positive JIAXS. If I give the arrow mark here, if it is like this, it is minus JIAXS. Now here it is, if it is plus JIAXS, the arrow mark would be like here. Previously it is like here now. So this is the perpendicular projection and this is what the arrow marks. Okay, you can see the plus minus, but you have to add the JIAXS drop to the EF2 to get the V. Okay, now this is JIAXS. Now project it onto the perpendicular to get the intersection point so that you can get the IA. Sorry. This is IA2. Now IA2 and this is theta 2 and this is EF2 and this one would be delta 2. Now we have got the EF2, delta 2, IA2 and theta 2 comma V constant. Now in this condition, let's write here itself what is the condition, overexcited or underexcited. See, this is the EF2, it is definitely more than V. This is overexcited. What is the power factor for this overexcited condition? EF2 is this IA2. Now this is V. The theta 2 is on top of V. So it would be definitely a leading power factor. Now let's reduce the field current. This is the last case which we will be looking at in the synchronous motor operation. So here IF1, IF will reduce, IF reduce, EF will be reduced. So it is under excited condition. Now my EF would be somewhere here. Okay. The tip of EF should remain on this condition, EF3. And EF3 again this one should be the JIAXS, JIA3XS. In fact, this is IA2, this is IA1, JIA3. So this is the perpendicular and I will just project it on the locus and this is the intersection point. Okay. And if you join the point here, you will have the IA3. Now, the power factor angle will be between this one, V and I, and EF3 is this one, and the angle will be between EF3 and V would be delta 3. Okay, it's a bit clumsy here, but I hope you got the point. Now let's write the over-excited and under-excited condition. Once we reduce that, the operating points, let's write the operating points here first. EF3, delta 3, IA3, theta 3, and V, and the operating points are here. Now see, where is IF3? IF3 is here. The length is definitely less than V. Now it is a under-excited condition. So what is the power factor? Theta 3 is lagging V. So it is a lagging power factor. So the starting condition also we have started with a lagging condition only. EF1, if you see EF1 here is also under excited. Okay. So this is what a motor condition would look like, and if I want to draw a V curve for a synchronous motor, same concept, variation of field current, we will see what happens to the IA. Now there exists one point such that this, if you look at this, okay, I will draw it here again. Now this is V, now it is IA, and this locus, this is the locus where IA needs to be, and this is lagging, and this is leading, and this is the unity power factor, IA, IA2, IA1. So IA1 is at a lagging power factor, IA2 is leading, IA will be at the unity power factor, where the length of IA would be minimum. So this point you will have the minimum, and if you reduce the field excitation from there, what happens to the IA if you reduce? Let's see. If you reduce your EF1 would be like this, EF1 and EA3, IA1, IA3 will be like this. If you reduce it further, you will have like this currents. So it is IA length would be, if this is the minimum point, IA length would be increased. Okay. Now if you increase the excitation, you have increased the IF. So it is EF1 would be increased. So EF2 is actually on top IA2. If you increase the EF, you will get IS on top of it, somewhere around this one. So here also you will have a curve like this. Now this is unity power factor, and this is over-excited. This won't change, over-excited, under-excited, because increasing IF is over-excitation. Excitation we are actually increasing. Reducing IF means under-excited condition. So usually this point is called normal excitation. That's the term they use. Normal excitation means neither over-excited nor under-excited, the operating part where it is the unity power factor. Okay, now let's look at the power factors now. What is this condition and what is this condition? So let's look at the conclusions we have drawn here. So wherever it is over-excited, we got a leading power factor. So this is EF2 is over-excited, IA2 is corresponding here, it has a leading power factor. Now the over-excited condition will have a leading power factor. So then correspondingly under-excited will have a lagging power factor. Let's confirm. Under-excited condition will have a lagging power factor. Here EF1 and EF3 are under-excited. That's why IA3 and IA1 are below, and theta 1 and theta 3 you can see it is lagging the bus voltage, and it is a lagging power factor. So this is what a V curve for a synchronous motor would look like, and here let's draw the write the conclusion here. For a synchronous motor, again two conditions are there: over-excited, under-excited condition. And over-excited for a synchronous motor is having a leading power factor. Under excited for a synchronous motor is having a lagging power factor. This is also important conclusion which you have to remember or which you can understand so that you can remember this. Okay. Now we have seen the excitations effect of variation of excitation for a synchronous motor as well as a synchronous generator, and we have derived the V curves for the same, and we have located the power factors for it. But what is the actual application of it? So where do we actually use it? Now we will discuss a very interesting case here. If you see the synchronous motor, it is having a very nice property. From the conclusions which you have drawn, it's right in front of us. If you see, this is a nice property of the synchronous motor that when you use this motor to from the tree diagram, you can see you can use this synchronous motor to draw a leading power factor current. So see, it will always draw a leading power factor current. This synchronous motor we have, if you operate that motor as a over-excited condition, right? Okay, that I can say. But what is the use of it? Where do I need this leading power factor current? Can anyone tell where the leading power factor is required? It's very useful for us. Okay. So what in previous days what it was done usually is let's say you have a big factory and okay, so let's say this is you have a factory here. I mean, why we're discussing this is because previously overexcited synchronous motor was considered to be as a capacitor case. Here we have seen this overexcited synchronous motor will draw a leading power factor. Usually, which component will draw a leading power factor? Capacitor, because inductor will draw a lagging power factor current. Now, that's why synchronous motor operating as an overexcited condition, people usually treat it as a capacitor since it always draws a leading current. Now, if you connect this particular synchronous motor which is over excited or a capacitor across any line, it will always draw leading current. And whatever load it is connected to, if you connect some load to the synchronous motor and operate it in an over excited condition, it will draw the leading power factor current from the supply, and it will supply to the load, whatever load is connected to it. Now, let's say you have a factory like this. Okay, now I want to improve the power factor of this factory. Whatever loads, whatever machines are in it, I want a very good power factor. So that is very important because based on the power factor only they will be charged, right? So if I mean, what usually a factory has a large induction motors. You can see in the factories power plants now. Mostly they use induction machines. Why? Because of the rugged construction, its maintenance is very less, and it can rotate at different speeds, speed control. We all discussed all this in the previous weeks. But usually, many industries will have this kind of induction machines and all, which are always a lagging loads. Sorry. So, machine can never operate at a leading power factor. That we already know. Now, my factory is drawing a lagging current from the grid. What is this grid? This is the government grid. Okay. Now you have a factory. You need supply from it to supply the loads in your factory, and you are taking supply from the government. Now, government will always observe what kind of current you are drawing because you are bound to the government. And now government will see, okay, this particular factory is drawing a huge lagging current. So when it is a lagging current, obviously you have a poor power factor. Whenever you have a poor power factor and also drawing a lagging current, your charges will be very high because you are drawing a very lagging current, and if your power factor is also poor, so you will be charged high because it's not a good thing to run a factory at very poor power factor. So power factors needs to improve their factories needs to improve their power factor. So in that application, this synchronous motor concept is very, very useful. And just now we also discussed, if you can operate your synchronous motor at the over excited condition, you will definitely draw a leading power factor current. Okay. So since it is always better to operate your factory close to UPF. If it is a unity power factory, it's well and good, but it can't be very exactly UPF. But it's better instead of operating at a poor power factor. It's better if you operate it at a close to unity power factor. Okay. So what we will do? This is the actual motor before. Now it is drawing some lagging power factor. So if now in this condition, let's say this is my voltage bus and it is drawing some I lag. So this particular current I'm showing. So this is a power factor. This is a lagging power factor, very poor power factor. Now this is a poor power factor. Now what we will do? Then we will connect some capacitor at the supply terminals and let's draw some leading because let forget about synchronous motor. Now I'm just connecting a capacitor because capacitor will always draw a leading current. Okay, now I have connected a capacitor. I'm just seeing previously capacitors were used in this case, but right now they are replaced with synchronous motor at the over excited condition. I will tell you why it is. Okay, okay. You can also say that why to replace a motor? We can just also connect a simple capacitor that will do the purpose. Okay. Anyhow, we'll come to that point. So, okay. Now I have connected capacitor. Now this capacitor will also draw the current from the supply. Now in this condition, it will draw some leading current. Definitely, it will draw some leading current, and it is a capacitor. It is exactly perpendicular JIA axis, right? This is whatever it's the impedance of that. Now this is old one, right? Now after connecting the capacitor, if this is the supply and this is the I lag, this remains same. Whatever load you have to supply, it has to draw that current. Now there is a small leading current which by the capacitor, you can say it as IC. Sorry. Okay. Now what is the new power factor resultant of these two? And this is the I resultant, and the new power factor is theta 2. Previously is theta 1, which is poor power factor. Now previously it is theta, this one, more theta, poor power factor, and now it's reduced theta. Now your power factor is improved, right? Because of the addition of the capacitor. Okay, now we have improved the power factor, well and good, you have the capacitor and all. But for the reason why we have added this capacitor is, let's say this have a x farads x microfarad capacitances you have added, so that it will negate the effect of this lagging and it will do some leading and it will close to unity power factor. So for this value of lagging current, this capacitor is needed to achieve a unity power factor. What if factory means you have different kinds of load? The load requirement won't be same always. Now if the is load requirement changes, now IA changes. Now if IA changes, the leading current, this is the lagging IA lag, which it will drop from the supply, it will change. So if IA changes, the leading current which you have to supply, which you have to get from the capacitor to make it close to UPF, unity power factor, will also change. So that will require a capacitance of another value. Let's say it is 5 microfarad now. So whenever your load keeps on changing, you have to add another capacitor, you have to remove it, you have to add it. So every time you have to change the capacitor. So that's the problem with adding this capacitor back. Now, what people are doing now? They are replacing this capacitor with this is a factory and this is the supply, and they are replacing it with a synchronous motor. It will draw lagging current supply. If you operate the synchronous motor at overexcited condition, we already saw synchronous motor at overexcited condition will draw a leading power factor current. Now it will draw a leading power factor current. Okay. Now it will compensate to the power factor and it will improve the power factor. But what advantage we have got here? You just have to uh, change the excitation current such that it will draw a different amount of IA, because that you always can change. You just vary the field current here. If the load requirement is, if this I lag changes, the corresponding lead you can get by just varying the field excitation. That's what we discussed till now. Okay. But it has to be always in the overexcited state. In that area, we have to vary the field current so that we can get the different lead current, leading currents by that. Now, earlier people used to connect these kind of capacitors, but if as we discussed, if the load changes, capacitor needs to be replaced every now and then. That's why every time you need to connect different capacitors. Now, as we replace these capacitances with a synchronous motor, and we will adjust its field current such that it will always draw a leading current. That is, we will keep it in the overexcited state, almost 90% leading current, because it's a capacitor kind of thing. It should do. Now we will call this condition. This phrase you will come across in many numericals, like whenever we are using a synchronous motor to supply a leading current, we will call this kind of motor as a synchronous condenser. So whenever you use a synchronous motor to supply a leading current, we call it as a synchronous condenser. It is nothing but it's serving the purpose as a capacitor. So it will draw the uh, leading current. And what else we can do? It's not just there for a leading current draw, but you can also connect some loads to this one. This is already a motor. It will not only draw leading current and it will maintain unity power factor, close to unity power factor, but also it will draw its mechanical loads, whatever it is connected to it. So it will supply both mechanical loads as well as it provides the leading current. So I hope you have understood this effect of variation of excitation to the synchronous generator and motor. See, it's very simple concept. When we start with the synchronous motor, we already discussed that synchronous motor is very simple topic. The analysis part is very simple. The phasor diagrams, equivalent circuit is very simple compared to induction machines. It's just you have to understand the concept very well. Now, today we have discussed the concept of variation of field current in the synchronous machine. We have discussed for both synchronous machine as well as the synchronous generator, and then we have seen the application of this, where exactly we will use this kind of application. Now, with this, I would let's let's discuss the problems. Uh, the problems. Okay, 1 second. Okay, I think problems are missing. Anyhow, I know the problems. I will just discuss with you. So the question would be the first. Hello. Yes, Anil. Yeah. Yeah.
So, cannot we use synchronous generator for improving power factor in place of synchronous motor?
Okay, you are saying that in place of synchronous motor, you want to use synchronous generator.
Yes, sir.
No, yeah, you can use that, but the problem with synchronous generator is it has to supply back to the load. You have to generate again. For generator, what you have to do, you have to give a prime mover input. You have to rotate it, and that is another mechanical energy you have to give it. But if it's a synchronous motor,
Yes, sir.
whatever supply you are giving to factory, it will just take a little bit of supply from the supply itself. You don't have to provide another mechanical prime mover rotation to it. And also in the synchronous generator, you are supplying to the bus, but here we are not giving to the grid, but we are taking back from the grid such that the summation of IA and also the IC would give a resultant current which is close to infinity power factor. So that won't work in case of synchronous generator in that way. Okay. So the first question which we will be solving today is it's a theory question, and the theory question is the underexcited synchronous generator would be delivering A, would be delivering power at leading power factor or delivering power at a lagging power factor. So what would be the answer for this? Can anyone tell? It's very simple. Under-excited synchronous generator will deliver leading or lagging. So someone. So Sai has said that it's B. B means it is delivering a lagging power factor. Is it correct? See, synchronous generator actually in the under-excited state, it delivers power at a leading power factor. It's not lagging. A. Its option is A. Okay, we just now discussed it. Synchronous generator under excited condition, it will draw a leading power factor. What's the confusion, Sai Krish? See, the answer is the under excited synchronous generator would always draw a leading power leading power factor. Okay, let's see the next question. These kind of theoretical bits are very common in gate exams. I want everyone of you to pay attention while solving these kind of questions. It's not just selecting leading power factor, lagging power factor. You just analyze the question. It is under-excited and it's a generator. You just imagine the phasor diagram. By looking at the question, you just have to imagine all like you just have to draw the phasor diagram in mind. This is the V and it is given under-excited. So EF would be before V, and if it's a generator, E would be V plus IA. So V and IA would be like this, and projection of IA after everything should be calculated in such way. So then you will get IA would be on top, and you can see that it's a leading power factor. So you have to take time. You just think for a bit and then answer. Okay, because we have discussed the same thing for the last 1 hour, and you can just say that analyze it. It's A or B without thinking. Okay, just have to analyze it. So next question, we will solve a small numerical, and Let's say we were given a synchronous motor with a synchronous impedance of 0.2 plus 2J ohms per phase, and the bus voltage is given as 440 volts line to line. This is the bus voltage, and it is said that my synchronous motor is acting as a synchronous condenser, we have discussed it. Let me just put the question here. Okay. Okay, so let's read the question along with me, and please take out your calculators as well and pen and paper too. So we were there with a round rotor star connected synchronous motor. So it is having a synchronous impedance of 0.2 plus 2J ohms per phase. And for the purpose of power factor improvement in the plant, that's what we just discussed. So for the purpose of power factor improvement, we are using this motor as a synchronous condenser. So there is no mechanical load for the motor. So it is operating at no load. It's just whatever losses it has, that is only the real power it will have to deliver. Okay. So it is required to draw minus 25 kVAR reactive power from a 440 volts line to line bus. So it is exactly the case which we have discussed right now, and it is saying that, let's say we have a synchronous motor. It has both the resistance part and also the reactance part. It is 0.2 plus 2J, and this is the excitation voltage, and this is a motor. Motor means it will draw the current from the supply. Okay. Now, it is said that there is no load over here. It is not delivering any load, but it's just whatever losses it has to deliver. Okay. And it is required to draw minus 25 kVAR reactive power. Now, we already said that if there is a factory and we have connected a synchronous motor, it has to draw from some leading power factor current. So what we call it as a reactive power. That is what capacitor usually draws. So if it is a lagging one, it is a inductive. It will draw, and if it is a leading, it is a capacitive circuit. Okay. Now we are given that my synchronous impedance is what, 0.2 plus 2J, and my Q, which is reactive power, drawn is minus 25 kVAR. Minus J 25 kVAR. Minus J represents the capacitive, and minus represents it is actually drawing the capacitive active power. So it is already mentioned here. The minus sign is used to indicate that it needs to draw capacitive reactive power at a leading power factor. So minus 25 kVAR. kVAR is kilovolt ampere hour. Kilovolt ampere reactive. So okay, and it's a 440 volts line to line bus. So V line is equals to 440 volts. Okay. Now what else is asked? It has a constant loss of 1 kilowatt. So there is no mechanical load, but whatever P, that is 1 kilowatt hour. This is the all power, real power it has. Now what we have to calculate, the first question is we have to calculate the line current. So whatever the current it is drawing from the line, we have to calculate. However, this is a phase per phase equivalent circuit, and however, it is a star connected synchronous motor, right? In the problem it is given, it is star connected. So the line current is same as the phase current. Okay. Now let's write the basic equation of a synchronous motor. What is synchronous motor? V is equals to EF plus whatever is the drop, IA ZS drop. So from here we can we calculate the IA, because we know V, we know ZS, but we don't know EF. So we can't calculate IA from here, but we have to find another way to calculate the IA. So what is another way to calculate IA? Any idea? We are provided with powers as an additional information. If you have any idea, we can proceed with that. So complex power drawn by the motor S, we know it is P minus JQ, minus because it is drawing the reactive power P minus JQ, because we know it is a S is apparent power is nothing but the P real power and also the reactive power phasor P minus JQ. From this we know P, we know Q, we can calculate the apparent power, but we need line current from this. So what extra information we can get? We know that another formula for complex power is 3 V phase I phase star, 3 VI star, right? That is a per phase quantities. Now this is what we want, and V phase we already know because we are given with a line voltage. From that we can get the phase voltage, and we substitute 3 V phase I phase here, and we already know P and Q. From that we can get, right? 3 multiplied by V phase would be 440 divided by root 3 multiplied by I phase star is actually equal to P minus JQ. What is P? 1 kilowatt, 1000 minus JQ is 25 kilovolt ampere. This one. So please solve this to get I phase star. I will also calculate with you. So what is I phase star? I phase star would be 1000 minus J 25,000 divided by 3 into 440 divided by root 3. Okay, please calculate this. I got I phase star as 32.83 at an angle of minus 87.70 amperes. Okay. Did anyone got the same answer? Okay. This is anyhow I phase star. We need I phase current. This is the complex conjugate. Take the conjugate of this one. We just have to multiply the angle with minus 87.70 amps. So this is itself is the line current anyway. This is star connected one. I phase is equals to I line is equals to this much. Okay. This is what the first question is. Line current will be dash amperes. Now the next question is the required excitation voltage per phase is. So we are actually asked this EF. What is the excitation? So since now we know V, IA and ZS, substitute all values here only. We will get right. So second question, EF is equals to V minus IA ZS. So what is V? It's all phase values per phase equivalent circuit. 440 by root 3 minus IF is this much, 32.83 at an angle 87.70 multiplied by ZS is 0.2 plus J2. So calculate how much is the excitation voltage. This value 65.98 at an angle of minus 3.41. Sorry, it's minus angle. No? Okay, sorry. So it's wrong. 32.83 at an angle 87.7 multiplied by zero point 0.2 plus 2j. 65.98 at an angle of 171. 171.98. Now we have to subtract it from the 440 by 3. So the answer I have got is, please tally with me, 319.51 at an angle of minus 1.649. This will be the volts. This is the required amount of excitation per phase we need. 319.51 volts at an angle of minus 1.64. Okay, this is what excitation voltage we write. We have to write the magnitude of the voltage here, magnitude of current, and the power angle delta will be, delta is what, and what, enter a positive number ignoring the sign. So whatever delta is nothing but the angle between voltage and also the EF. So this is V, this is EF, this is the angle. Okay, and yeah, we can see EF is at an angle of minus. Minus means if it is V at an angle of 0, EF is below. So that's the nature of motor. EF will always be below 1.649. That is the value of the delta. Delta is 1.649. Okay, what's the next question? Uh, so can anyone tell what is this, an under excited machine or the over excited machine? Is it under excited or over excited? Anyone? So it's a over excited machine. How can you say that? Over excitation, under excitation will only be set based on the length of EF and the V. Here the V per phase phasor, if you see, V is nothing but 440 by root 3. That will give you 254.03 at an angle of 0 degrees. And EF you got it as a 319.51 at an angle of minus 319.51. It is 1.649 degrees. So it is, EF length is more than the V. That's why it is a over excited machine. So yeah, with this problem, I hope you will it will help you in solving the assignment problem for this week. And some more concepts on synchronous motor and also some more problems which are related to your assignment will be discussed in the next immediate session. Yeah. So this is what today's discussion would be. To have a quick summary of today's discussion, I will just quickly go through all the discussions we have done today. So we have started with the concept of analyzing the effect of variation of excitation, that is the field current, and we have seen the boundary conditions for it. If we fix the output power, Ia cos theta and EF sin delta, these two products should be constant. With that, we develop the phasor diagrams for by increasing the field current, by decreasing the field current, and analyzing the over-excited, under-excited condition, as well as the power factor that it is drawing or delivering. And the first we did for the synchronous generator, and we have arrived at the V curves, which are very important concepts for synchronous machines. And then we have replicated the same condition for the same analysis for the synchronous motor. Synchronous motor also we have done the operating points, previous operating points, and increase the field current, reduce the field current, and we have seen the phasor diagrams. And then we have arrived at the same conclusions for the synchronous motor and also the V curves for the synchronous motor. And yeah, after that we discuss the concept of the application, where we will be utilizing this concept of improving the power factor, and it is very important concept for the industries where most of the loads are lagging. There it will be very handy to use such kind of synchronous condensers, where it will help in drawing the leading power factor, so that the overall power factor will be close to unity, power factor. And then we discussed a few problems, and these are theoretical bits. And please don't make mistakes in this simple questions. What is an underexcited synchronous generator motor will do? Will it deliver a power at leading power factor? Will it deliver a power lagging power factor? They will ask n number of combinations from it. There are different combinations. Overexcited synchronous motor, underexcited synchronous motor, overexcited synchronous generator. Will it deliver a lagging power factor or a leading? Everything. It should be very easy. We just draw the V curve and everything would be solved. And then we solved a problem where actual application we have seen they are using the synchronous motor for improving the power factor. Here they have used it as a synchronous condenser, and then we have calculated the basic line current, excitation voltage, delta, and estimated the state of the motor. So if you have any doubts in this session, please do ask. And I hope this is the last session. Uh, Yeah, okay, Sai Krish. Sai Krish. No problem, no problem. Yeah, it's fine. It's good that you have interacted. It's okay. I hope, yeah, this is the last session for this Electrical Machines 2 course. I hope you all had some kind of useful discussion with me, and I hope at least some questions or some discussion points you have found it useful in these 12 weeks of discussion. And I would wish you all a very best for the examinations which will be going to happen soon. And meanwhile, if you are having any doubts, please refer to the recordings and also the brush up all the solved assignments questions and go through the solutions and go through the discussions we have discussed every week. And please don't miss the next 79 session. You will be discussing some more concepts on synchronous machines. So yeah, thank you all for coming to this session for whole 12 weeks. Yes,
Actually,
yeah.
in the NPTEL portal, they gave the online calculator link. In that, how to use for getting the polar to rectangle conversion or rectangle to polar conversion. The traditional method, what we are following is we know that square root of a square plus b square for getting the magnitude and the angle is tan inverse of b by a. Like that only we have to use or we have a direct conversion method in that online calculator.
I am not aware of the online calculator. If you have the link, can you send it to me?
Actually, in the announcement column, they gave one link for online calculator, so we can use it for demo purpose.
Okay. Usually in the online calculators, I don't think the polar form would be there. You have to do it. Okay. I think you have to do it by the calculation of this only. Under root a square plus b square and all. So I don't see any polar to rectangular here. No, this won't do the uh, this won't be useful. Yeah, the thing you have said that only you have to do tan inverse. Are there trigonometric expressions here at least? Okay, yeah. So yes, no, this won't work for the polar rectangular conversion. Okay, once again, thank you all, and this is the last session, and thank you everyone for attending for the last 12 weeks and patiently listening and interacting with me. Thank you all. Thanks for joining, and we will see in next course or some other year if we meet, and we can meet in the another NPTEL course. Thank you all.
Thank
Thank
you.
you, Anil.